We've already seen one form of the Arrhenius equation, which says that the rate constant k is equal to the frequency factor A times e to the negative EA over RT, where EA is the activation energy, R is the gas constant, and T is the temperature. There are other forms of the Arrhenius equation which you might want to use depending on the problem. So let's go ahead and find those other forms. And we start by taking the natural log of both sides. So we would get the natural log of k is equal to the natural log of A times e to the negative EA over RT. So on the left side, we still have the natural log of k. And on the right side, we can use a log property. The natural log of A times e to the negative EA over RT is equal to the natural log of A plus the natural log of e to the negative EA over RT. And the natural log of e to the negative EA over RT would just be equal to negative EA over RT. So we can write that in here. The natural log of the rate constant k is equal to the natural log of A minus EA over RT. And I'm just going to rewrite this as natural log of k is equal to negative EA over R times 1 over T plus the natural log of A. And the reason I wrote it this way is it's easier to see the form y is equal to mx plus b. So y is equal to mx plus b. So if we graph the natural log of k on the y-axis and 1 over t on the x-axis, we're going to get a straight line, and the slope of that line, which of course is m, the slope of that line is equal to negative EA over R. So we can find the activation energy from the slope of the line. And if we wanted to find the frequency factor, right, we know that the y-intercept is equal to the natural log of A. So we could find the frequency factor if we wanted to. So this is another form of the Arrhenius equation. So I'll go ahead and box it here. So sometimes you might want to use this form. And we can figure out another form. So let's start with this equation that we just figured out, and let's write this for one specific temperature. So at one specific temperature, we're going to have a specific rate constant. So the natural log of K1, so I'll call this rate constant K1, is equal to negative EA over R times 1 over a specific temperature, T1. Right, so when the temperature is T1, we have rate constant K1. And so let's also put a natural log of A in here. All right, let's use a different temperature. Let's say this is T2. Well, at a different temperature, we're going to have a different rate constant. So we'll call the rate constant K2. So the natural log of K2 is equal to negative EA over R times 1 over T2 this time, plus natural log of A. All right, so now we have two different equations here for two different temperatures with two different rate constants. Let's take the natural log of K2 minus the natural log of K1. So let's go ahead and write that. So the natural log of K2 would be all of this right here. So let's write that in. Negative EA over R times 1 over T2 plus natural log of A. Next, from that, we're going to subtract, right? So subtract the natural log of K1. And the natural log of K1 is all of this. Right, so this would be minus, and let's put all this in parentheses, negative EA over R, 1 over T1, plus the natural log of A. Next, on the left side, we can use a log property. Right, so over here on the left, natural log of K2 minus natural log of K1 is equal to the natural log of K2 over K1. Again, that's a log property. And on the right, we would have, this would be negative EA over R, 1 over T2 plus natural log of A. And then we have these two negative signs here, so that would be plus EA over R, 1 over T1. And then this would be a negative natural log of A, so a negative natural log of A, so minus natural log of A. Notice the natural logs of A go away here. All right, and let's write this next form of our Arrhenius equation. So on the left side we have natural log of K2 over K1 is equal to, let's pull out a negative EA over R. So if we pull out a negative EA over R, then we would have 1 over T2 minus, we need a minus sign here, 1 over T1. So that's just some algebra. And we've derived at another form of the Arrhenius equation. So the nice thing about this form is there's no longer an A in there. Right? So if we know the rate constants at two different temperatures, right? If we know rate constants at two different temperatures, we can find the activation energy. So here are some more forms of the Arrhenius equation, and in the next video we'll see when to use which form. And you might even see a different form than this, right? So this is how I wrote it, but different textbooks might have different things on the right side of this equation. So use whichever one you like the best.